We are ready for the final talk of the day, which is invited talk by Barriga Acosta, who will be telling us about weak pseudo-radiality of CST spaces. Too much. Thank you.
All right. So let's see what's going on with these properties and these kind of spaces. Okay. So let me first say something. So in the spring topology, that was in spring in Texas, I decided to share some pictures for people that are joining the Zoom meetings from home, and I received like a good feedback. So I will not do the same. So these pictures are for people at home. This is a random tree that I found very beautiful because it's kind of lean, you know, and then these branches are kind of in the opposite direction. Yeah, I guess it's just a phenomenon of the wind, I think. And this is right outside of this building. This is the architecture in general of this Chapman University. It's pretty, and I found these stones that are right here as well. And there are basically some statements that I find interesting, but I have a question, like an open problem, like why this spiritual was the only one with water. I'm gonna leave California with that. And these topics were about spirituality, intellectual, physical, and social aspects of life. Then last night we went to experience this amazing sunset, right? California has beautiful beaches, and we gathered, the organizers gathered people in this beach, Laguna Beach. It was a lovely evening. We started listening to music and having food, taquitos, steak taquitos with guacamole and salsa and cheese and grilled vegetables and whatnot. And then we start drinking just water and soda, and we have fun, right? All right, so that's it for people at home. And now I have to talk about math. My math is gonna be non-algebra related, unfortunately for you. But another propaganda too is that the next conference, the last conference, is going to be in North Carolina. So I hope to see you there. And then I can show you the theory around. It's gonna be cool. All right. So my talk is in the field of sector topology. So I'm going to use a lot of these things. For example, the cardinal invariant of the continuum. So these are just numbers, uncountable numbers that we can define based on combinatorial properties of the natural numbers. For example, this number right here. So an almost disjoint family is a collection of subsets of omega, so that pairwise are finite. The intersection of two of them is finite. Then we can define this number. This number is called the almost disjoint number. If you take a family satisfying this property, being almost disjoint, you can take the minimum cardinality of a maximal family of this type. Right? It is a property, a consequence that this number or this cardinal lies between omega-1 and the continuum. Of course, we have this upper bound, the continuum, right? Because of this inclusion. And if you have a countable almost disjoint family, you can diagonalize this family to create another almost disjoint member of this family, contradicting maximality, right? So maximality here is important in order to be greater than omega-1. Okay, and it looks like that. That number is on this range. So if you agree with me, this guy sometimes is this one and sometimes not. right? That's the continuum hypothesis and the negation. And just like this number A, the almost adjoint number, we have a lot more. All of these are cardinal invariants of the continuum. Two of them, the bounding number and the dominating number, are following me, are seeking me, and pursuing me in any problem that I work on. But recently, this one, which is clearly number, is in my life, in my dreams. And the list, this is the alphabet, and many more are taken. For example, N is taken, but I don't remember the name and the description. Z is taken for sure, and a couple more. I've never seen F being defined as satisfying a property on the natural numbers. So if you are able to define a number like this, I'll be happy to include it in my presentation. All right. So this talk is gonna have several ingredients. One of them, as I mentioned, is this cardinal invariant. So uncountable numbers. Another is sequences. All right. So in calculus 1, we were taught that there are points being like the limit of a sequence, right? But this concept is a concept of proximity. Like you are approximating this point over here with this collection, and this means they're getting closer and closer. Right? So then they introduce the concept of a convergent sequence. And in this sense, Frechet, I just wrote this name over here, meaning that for any open ball around this center, we're going to include all of them but final many. So this notion over here of having all of them but final many is like the condensation of this collection is high around this ball, right? Then we start defining more definitions. We start stating more definitions like the Cauchy sequence. It doesn't talk about this limit point, but it talks about the elements in the sequence, right? So they're getting closer and closer from each other. And then this more topological abstract definition of the sequence. And in general, there are a bunch of these properties in relation to sequences. There are definitions involving sequences, for example, sequential compactness, sequential space, Frechet horizon, radiality, pseudo-radiality. We're going to focus on this one. And then there are convergence under the presence of some other topological properties. For example, compactness, like over here, numerability axioms, like for example, being first countable, linear orders, which is part of this analysis too, the reals, and metric. So over here in calculus 1, they didn't tell us, oh, because there is a linear order or because there is a metric, right? So if we start separating all these concepts, we can analyze sequences in every and each of these topological aspects. All right, so sequences are going to be another ingredient. And the last ingredient is forcing. So forcing is a technique. It's a technique to create models of ZFC. All right, so I'm going to start talking about philosophy a little bit. Forcing was invented by this Mr. Cohen, passed away recently. And actually, he was working with algebra and real analysis. He wanted to do something in this field, and he ended up doing like a very deep set theory. So this is how it works. We know that ZFC, or the mathematics, cannot prove, they cannot provide a model for itself. This is one of the Gödel's results. But we all assume they're models for these actions of ZFC. So we believe ZFC is consistent. If consistent, it means there's a model for this theory. All right. Then another This is called a notion of forcing. A forcing notion is just a poset. And for me, I like to think about these guys. The elements in this collection are like promises. You want to attain or achieve a goal, and these are just promises. All right, the elements over here. All right, so these promises are what are forcing. They carry information and they know things about stuff in general. And this symbol is called P forces blah, blah, blah. P forces a property is because they know information. But I just like to call them promises. All right, they're trying to approximate an object, and this object is going to be a subset of this partial order. But as an element, it doesn't live in this universe. It's a subcollection of the partial order, but as an element, it doesn't live over here. It lives somewhere else, and it is valid, and it is very well defined. And this is what they call the forcing theorem. The existence of this subcollection is valid by this theorem. Now, this collection is going to be a filter, and it is what we call a generic filter for this poset. A general filter means that it's going to intersect every anti-chain of this poset, whatever. But these guys, these promises are approximating this filter over here. Right? Now, this guy doesn't live in this universe. It means it lives somewhere else. It's going to live in a bigger extension, a bigger model containing this one. Because this guy, V attached G, contains V and contains this new element. And a lot of weird things can happen over here. Example, this poset by Cohen, it is called the Cohen poset. This is defined by partial, let me move this over here. If we take the collection of finite partial functions from omega to omega, these are going to be the promises. And what is the thing that we are approximating? So if we have a generic filter on this poset, those promises are coherent with each other. They don't contradict each other. So partial functions, we can take the union of all this collection, and that's going to be a new function from omega to omega, a total function from omega to omega. It turns out that this function associated to this filter doesn't belong to this universe. It is a new real number, right? So Paul Cohen used this technique to come up with a bunch of new real numbers over this model and breaking the continuum hypothesis. So you're going to start adding a real number over a real number, let's say omega-2 real numbers, and there you go. You broke the continuum hypothesis. So this is basically how it works. You start with your model, have a poset. These poset, the collection of these elements are promises. They're trying to approximate some object, and then over here you can tell properties about the object. Not over here because we don't live in this universe. We can just name the properties over here from the ground model. That's another weird part of forcing that. We don't touch these objects, but we see them and we can just talk about them. And in order to talk about them, we need names. And all the names live over here. So this object, we don't know it, but we can talk about that object. That's enough. All right, this is a unreal. And then if we understand this behavior, like one step, right, extension, we can do the same. So over here, let's say we have introduced this new object, the generic filter G, for this poset P, and then in this new extension, we can have another poset and have another generic filter H for Q and have another bigger extension. This is what we call an iteration. And notice that I'm adding this dot over there. This is what I'm referring as a name. This object Q, posted Q, lives in the intermediate extension. It is an object that we cannot touch, but we can talk about it as a name. That's why we add this dot on top of the objects. It's just one way to talk about them. And over here we can take products of poses, etc. But both, in this case, both have to live in the ground mode. This is another way to have a partial order, and it looks like this, like a two-step iteration of partial orders. A big part of forcing is that maybe this G has a certain property, but when you add another generic filter, maybe that property is going to be destroyed in the next step. A lot of weird things happen over here. There are terms that says, oh, one property is indestructible with this poset, or you can never kill this property. And then there are the preservation theorems, which is a huge part of enforcing. Well, this is the other part that we're going to need later on, and then we can take iterations of any length under the same behavior, right? Okay, so I'm going to begin with my talk now. And this Jazz, where's Jazz? I don't think Jazz is here, but he mentioned, why do we do what we do? Why is this important, right? So pseudo-radiality is one of those definitions of sequences. Most of the work was done in the 80s, and it kind of stopped in the 2000. Because there were not enough tools to keep digging in until, I guess, now. That with joint work with Alan Dow, he came up with really nice ideas involving forcing sequences and elementary submodels that I'm going to talk about later on. So, sequential compact space is a space satisfying that every sequence in there has a convergent subsequence. It's just one of those definitions regarding sequences. Beta omega, the check-stone compactification of the natural numbers, is compact, but is not sequentially compact. Meaning there are no convergent sequences in this space. So this is just one example that tells you, no, compactness does not imply sequential compact. And the other way around, omega 1 with the order topology is sequentially compact and non-compact. This is because if you have any sequence, any countable set over here, the supremum, there's going to be a subsequence converging to the supremum of this collection, right? Okay, we're gonna need this concept too. So X is a topological space, and we take a subset of X. A is radially closed if no sequence within A converges out of A. In the sense, now over here, I'm not just talking about a countable sequence. I'm going to allow any sequence of any length. And the convergence, the definition of this convergence is basically that. If this converges out of A, it's going to converge to a point. Any neighborhood of this point has the biggest concentration of elements of that sequence, right? Meaning we're going to just leave out very few elements in this sequence, like kind of the Frechet behavior. But we're allowing here this sequence to be of any length. Now, the radial closure of this subset is a minimum radially closed set containing A. Okay? This set, the radial closure, is not necessarily closed. Then, definition, right? X is pseudo-radial if the radial closure of every subset is closed. So we are demanding this property about the radial closures, kind of capturing all the limit points with sequences, as limit points of sequences. Okay, That is, the radial closure coincides with the actual closure. And this is just another way to say the same thing. In other words, if capital A is non-closed, there is a sequence within A converging out of A. First countable spaces are pseudo-radial, ordinals are pseudo-radial, basically by the same reason of omega-1 being pseudo-radial. You take a sequence of any length, the supremum is going to be a limit point, there's going to be a subsequence converging to that point. All right. And, oh, by the way, so what is the difference between sequentially compact and pseudo-radiality? If you notice, this last statement for pseudo-radiality looks very similar to this statement formulated in the other direction, right? It doesn't matter. So what I'm trying to say is the real numbers are not sequentially compact because the natural numbers is a sequence that has no convergent sequence. But it's going to be the real numbers are pseudo-radial, they're first countable. So you can reach any point in the closure of any subset with a convergent sequence, countable convergent sequence within the subset. So the real numbers are pseudo-radial and they're not sequentially compact. Okay, but it turns out that under compactness, okay, sequentially compactness is going to be an equivalent to pseudo-radiality restricted to countable sets. Okay, so these properties, sequential compact and pseudo-radial are different in general, but if the space is compact, they are the same thing when we consider pseudo-radiality only for countable sets, meaning the sequences are allowed to be just countable, not of any length. All right, let's prove this fact just to warm up. All right, so let's prove this direction. We're assuming X is sequentially compact. And we want to prove take a countable set that is non-closed. So these dots over here are the collection A. It is non-closed. That means this point is not. This point does not belongs to the closure. It does not belong to A, right? This collection is countable. So we want to prove there is a sequence in A converging out of A. This point over here does not belong to A, right? So we can do this trick. Take neighborhoods around this point, like this, that are going to leave n many elements of this collection. So the n neighborhood is going to leave out n many elements in this collection. So this looks like it's a G delta set. The intersection of these neighborhoods is a G delta set. This G delta set concentrates around this point, and it doesn't touch the green points because we were meant to leave n many points at every step, right? So the intersection is going to leave all of them out. Now take the rings, and you're going to just pick one of each ring, one point of them. The space is sequentially compact. The x's are a sequence. There's going to be a convergent sequence, subsequence converging somewhere. But this subsequence is not allowed to converge to this set because the G delta set was concentrated out of this set, right? So this subsequence is going to converge somewhere else. Not to this point necessarily, it's going to converge to some point in the G delta set. All right, but the G delta set didn't touch A, is converging out of A. Okay. The other direction. The other direction, we want to prove X is sequentially compact. Okay, take your favorite sequence. There you go. This is a countable set. Because we are living in a compact space, it has an accumulating point. Well, take this collection and remove this point. In case this point belongs to this collection, just remove it. So the green collection is a countable collection and is non-closed. We're removing a limit point. Then there is a sequence within the green points converging out of there. That's your subset, converging subset. All right. So I want you to keep in mind that pseudo-radiality restricted to countable sets is basically sequential compactness in the class of compact spaces. They're the same thing. Right? The question, the big question in the 80s is assume compactness and sequential compactness. What else can you add? What other ingredients can you add to obtain full pseudo-radiality? So the property for sequences of any length, right? That is the big question. Shapirowski in the 90s proved that under CH, you don't require anything else. Compact sequential compactness is enough to have full pseudo-radiality. Right? Well, you don't need anything else. You are abusing a lot, right? With CH. Then you have and semi-closed 3 years later, they wiggle a little bit by letting the continuum to be at most Aleph 2, and they have the same consequence. They prove a couple of more examples, very interesting examples. This one says, if you have your space that is compact and non-pseudo-radial, then there is a small set in which being not pseudo-radial happens. You're going to find a subset whose closure is not pseudo-radial, and this set has size less than the continuum. So whatever happens in being non-pseudo-radial, it happens in a small set. Small, quote unquote. And they left, this other result, it is consistent. That means there is a model of CFC. Satisfying that the continuum is Aleph 3, and there is a CSC space, which is non-pseudo-radial. So they're separating these two properties, right? Being sequential compactness under compactness, the class of compact spaces, and pseudo-radiality. Now, I'm highlighting this part, it is consistent. That doesn't mean that C, the continuum equals Aleph 3 implies this, right? It's just consistent. This means these two parts get along, they coexist, but not necessarily this implies this property. And actually that was a question left in that paper. Does C equals Aleph 3 implies that property? And 3 years later, Dow, Juhas, Sukuk, and Selmi-Closey answer no. So item B over here in the forcing extension by adding any number of coherent reals, we are experts with coherent reals now, over a model of CH, every CSC space is pseudo-radial. Okay, meaning if you add your model is a model of CH, get Aleph 3 coherent reals, add them with a forcing technique, and in this new model, every compact, sequentially compact space is going to be pseudo-radial, contradicting or denying answering in the negative form this question, right? So the continuum being Aleph 3 does not imply always this property, right? Another very interesting result is that they could replace the continuum in this result by the splitting number that I talked about in the first slides. All right, so this splitting number plays an important role in this topic. All right, then in the 2000, and this was probably one of the latest results of this topic, is they start focusing on separable subspaces. That is it true if you have a compact non-pseudo-radial space? Can you find a closed separable non-pseudo-radial space? And this means, can we improve this result even better to write here omega-1. Not only this splitting number, which is less equal than the continuum, but can we change here omega-1? That is basically this question. All right, and they answer yes if they assume this space, that this is the product with the product topology, the Tikhonov product of this space omega-2 times is not pseudo-radial. So this space is actually kind of weird. Why omega-2 over there? Well, Shapriovsky back in the 90s, he asked if it is true in CFC that this space is not pseudo-radial. It turns out that this is independent from CFC. With this model, in this model that we saw over here, right? They have that 2 to the omega-2 is not pseudo-radial. And in a model found by Alan Dow, this guy is pseudo-radial. And actually every compact space of weight and most omega-2 is pseudo-radial. So to answer this question is going to be independent as well from CFC, right? All right. So just to add more properties around pseudo-radiality, it's kind of this concept, this property is well studied, but there are many more between pseudo-radiality and sequential compact. So again, among the class of compact spaces, pseudo-radial implies this other property. So what is this? Closed separable subspaces are pseudo-radial. With the motivation of this theorem by Bella, Alan Dow, and Tironi. Okay, so I'm adding here separability. It is a fact that if we remove this word separable, just allowing closed subspaces are pseudo-radial, that is equivalent to being pseudo-radial. Right? That is homework for you. This homework for you. But we are adding just a property about countable sets, right? Okay. This implies also that the radial closure of countable sets are closed. The radial closure countable sets are closed. And we're going to name this property as being weakly pseudo-radial. So weakly over here because we're focusing on countable sets. Pseudo-radial means radial closures are closed. Weakly countable. Okay, and this in particular implies sequential compactness. So we are including two more properties between pseudo-radiality and sequential compactness. You know, mathematicians love to do this. And then they say, okay, we have a sequence of implications. What if we reverse them? Can we reverse them? Okay, let's begin. So under CH, we know Shapriovsky has all the power. We can go from 4 to 1. So all of them can be reversed. 4 to 3, it is enough to have this cardinal invariant. It is called the pseudo intersection number. This guy equals the continuum. You can reverse this one. This is in progress, and we're going to see it in the last part of this talk, that is going to be independent. This implication is going to be independent from CFC. Also, 3 doesn't imply 2, because in the model by Juhas Sendiklosi, it is consistent with this thing that this space is not pseudo-radial. This is a compact space. And over here, this splitting number that I didn't mention the definition, it has a topological version. This S, the splitting number, is the minimum power of 2, such that this space is not sequentially compact. So in this model, we have splitting number is Aleph 3, that means 2 to the Aleph 2, it is sequentially compact. So this guy is compact, sequentially compact, not pseudo-radial. Now, this guy is also separable. right? Separability is C-productive. That means that we're violating this property, right? A closed separable subspace is pseudo-radial. False. This is separable by itself and it's not pseudo-radial. And hence, and yes, it is sequentially compact and compact. I'm gonna take a break. Well, the last one is the hardest one. I haven't explored this question. If we can prove that this cannot be reversed, the first one. But for this, we will need a model in which 2 to the omega 2 is pseudo-radial. So I have homework to do. The Allen-Dow's model, I need to explore that paper. I haven't done it, but it's work for the future. All right. Now, the last thing we're gonna need for the main results are these stuff. And hopefully, these tools that I'm presenting, you leave California with an idea of how these work. And these are elementary submodels. Okay, I like to think about these objects as magical. They're very magical. All right, definition says, given two models, M and V, contained in V, M is an elementary submodel of V, I have a typo there. If any statement, any formula with parameters in M, that is true in the bigger model, it is also true in this smaller one. Right? Basically, they say the same true if there are parameters in M. Nice features of these elementary submodels. If you have this guy is countable, this is a countable ordinal. It looks like this. So this is the ordinals. If you have a countable elementary submodel, it's going to have an initial segment before omega 1. And then after omega 1, it can have like finally many elements among the ordinals. But this intersection is not trivial. I mean, it is a consequence, but it's not like very intuitive. This is an actual ordinal. If we take the intersection M with omega 2, this is not going to be an ordinal. It's going to be a subset of omega 2, but not an ordinal. Right? Another nice feature, if you have an element in your model, countable model, elementary submodel, and there is no bijection with omega and this guy in M, then M is going to think that A is uncountable. If M thinks something, the bigger model, which is the universe for us, is going to think the same thing because the parameters belong to M, right? Also notice that omega is always contained in M. Omega, the natural numbers, is always contained, and it also belongs to M. You can demand that. All right. Just to have a good flavor of elementary submodels and just to see the magic and the power of this. Do you recognize this lemma? The delta system lemma, right? Everyone knows about it. Okay, so how can we use elementary submodels to prove this? Okay, we have a family of finite sets. It is an uncountable family. We want to provide a subfamily, uncountable subfamily with a delta system, meaning there's going to be a root, and after this root, all these members are going to be pairwise disjoint. They only intersect in this root. That's a delta system. I have a typo, uncountable. Okay. Take your favorite countable elementary submodel. The intersection with omega 1 looks like this. It's an ordinal, right? Then this is very standard. Whenever you reach the maximum, you're gonna grab another element out of the elementary submodel and say things. So what we're saying here is we're gonna grab the A delta element in this family. Now this delta as ordinal does not belong to M. The supremum of this intersection, delta, does not belong to M. right? That's one property. This A delta is a finite set, right? We can assume that all these finite sets are subsets of omega 1. So this is a finite subset of omega 1. It has some part below M or below delta and some other finite part after delta. So call this part capital R. That's going to be the root for us. Consider the subcollection of this family, the subcollection of this family that is going to be maximal, and we're going to demand that this family is a delta system with root R. So we're grabbing all elements in here with this part as a root for a delta system. And then we want to have this family maximum. Maximality is important here. Right? Then, if there is a bijection, this is not capital A, this is capital B, the set of ordinals. If there is a bijection between omega and capital B in M, delta was part of this capital B. Then delta belongs to M, and that is a contradiction. All right? If there is a bijection, omega to capital B in M, delta belongs to M, that is a contradiction. If there is no bijection, then M knows that capital B is uncountable, and that is your delta system. All right, so notice that in 4 lines, working with elementary submodels is powerful. And if you have read the proof in CUNEN, in the textbook, it takes quite a lot to, all the steps. And all that machinery is kind of implicit in these models, as elementary models. All of those steps that you do, like finally many constructions, are included over here somehow. All right. Okay, I'm gonna start to hurry up. No. Okay, I'm going to the main result. Okay, so we have this result by Dow. You have circle and semi-closed, right? That says in any forcing extension by adding Cohen reals, we have this property. Every compact, sequentially compact space is pseudo-radial. So what we prove is that by some other poset, other class of posets, not only the Cohen poset. This is a bigger class, and the Cohen poset is one of these. That's all we need to know, right? Because this theorem, I want to mention that is an extension or a generalization of the previous one. So, we have a model of CH. In this result, we have a model of GCH. So it looks kind of stronger, but what I'm trying to say is that this is a true generalization of the previous one. So CH is implicit over here. And this combinatorial principle square is just for technicalities about singular cardinals. All right, we don't have to go into details. Then the Cohen poset satisfies this property, so we are analyzing a bigger class of posets. What we want to say is that in this extension, every compact, sequentially compact space is weakly pseudo-radial. Now over here, it doesn't look like we are generalizing the previous result because we are not reaching full pseudo-radiality. Only countable pseudo-radiality restricted to countable sets. However, if the splitting number, do you remember S? If the splitting number is below Aleph 2, then in this bigger extension, then sequential compactness reaches full pseudo-radiality. So in that sense, it is a generalization. Well, it doesn't really matter how the splitting number is active here. But what I want to show is the proof of this result, and just to show you how these type of proofs work in forcing extensions. So what we want to prove is that we have a compact, sequentially compact space over here. And this is happening in the extension, after forcing with this poset. All right. If we zoom out, in that extension, this is a space, and we can assume that this space is separable. What does it mean to be weakly pseudo-radial? The radial closure of any countable set is closed. So suppose this is your countable set, X is the closure of this countable set, right? X is gonna be the stone space of a Boolean algebra of this countable set. So I'm not saying omega is a discrete set over here. I'm just saying omega has certain topology, and we're taking the Boolean algebra of the open sets, a regular open sets, and then we take the stone space that is X. It is compact, sequentially compact. All right. So we want the radial closure of any countable set to be closed. If we take a point in the closure of this countable set, that point, by compactness, is the U limit for some ultrafilter on this countable set. It is just another way to say X is a limit point. When you have a limit point in the closure of a countable set, X always looks like this. It is a U limit for some ultrafilter. So what we want to show is that there's gonna be a sequence in this set converging to X. That means the radial closure of this countable set is closed. That's what we want to prove. The radial closure of this countable set is closed. And the technique for that is super nice. What we're gonna do is, we have here the ground model. This is the extension, and we're gonna grab an elementary submodel in the ground model. Assume, just for now, that the size of this elementary submodel is Aleph1. When you have an elementary submodel like that, you can split it as a chain of countable elementary submodels. It's an increasing chain. All right. So in the extension, over here happens a lot of things. So this is the extension of the universe by the poset satisfying the finally proper decay, B attached G, but we can do the same because this is a model. We can have M attached G. All right. In the extension, we have this space, right? Now, if we have one of these M alphas, this M alpha is countable and is part of that increasing sequence. M alpha intersected with the U, the ultrafilter, being this the U limit. This guy, we don't have any information about the ultrafilter. But when we take this intersection, this is a countable family of elements of U, a countable family of neighborhoods of this X. This is the intersection is going to be a G delta set. You can take a convergent sequence to some point in that G delta set. Why? Because we know that X is sequentially compact. So there is a convergent sequence converging somewhere in the G delta set. We're going to take all these sequences for each of these elementary submodels. All of them have a limit point, and it turns out that in the extension, there's a unique limit point coming from something like this. Right? So we have forcing extensions, elementary submodels, and sequences all combined together. And of course, with a lot of patience and a lot of work, we're doing this because we're not allowed to touch these objects. We're only allowed to talk about them. That is the hard part. What we're doing basically is we want to capture more and more information about that ultrafilter. What is the only thing we can do? Is start increasing the size of the elementary submodel. So we start with M size Aleph1. what we just did is to split this elementary submodel into countable elementary submodels. So in this level, on this level, all of them are countable, and each of them are providing limit points. And the collection of this sequence, this sequence is going to converge to this point, and this point is going to live in the radial closure of omega. So if we level up, we start having a bigger elementary submodel. We don't know what is the size of the ultrafilter, right? But imagine it has size Aleph 5. So we start increasing the size of the elementary submodel. What we're doing is creating a tree. Each node is giving you a limit point. And if you're leveling up these steps, you're producing limit points that are unique. And at the end, you're gonna reach this point with the radial closure of omega. So that's like the idea of this proof. The nice technique over here is elementary submodels with trees. And these are called Davis trees. So this is a very popular, it's getting popularity in set theory, but you don't have to read this. It is a nice paper. It is worth it to read, or at least to see the examples they have. But it's basically trees with elementary submodels, and you can, well, in this context, we could combine sequences and limit points based on these trees, right? One property is that these trees, every branch over here is going to be finite. Because we have a cardinal, and we're splitting this model until having a countable nodes. So we cannot have an infinite decreasing sequence of ordinals. So every branch is fine. Okay, I'm going to skip this part and jump to the second one, which is more forcing, unfortunately. So 4 implies 3. We wanted to come up with the negation of that implication, right? This comes from a matrix iteration, which is another part of forcing. All right. It is not really worth it to talk about this main result, but it's just going to give you the space, the appropriate space. A space that is going to be compact, sequentially compact, and not weakly pseudo-regular. So let's just believe that this result gives you what we want. But let me say, we have a descending mod finite family of size omega 1. The weight of x is going to be less than s. That's why x is going to be sequentially compact, because the splitting number definition. The family of the A alphas has no infinite pseudo intersection. These are just properties. So x have what we want. The closure of x, the closure of the A alphas in x are clopen. This x is going to be a compactification of omega. So number 3 is basically telling you A alpha is a subset of omega, but it's going to be part of a Boolean algebra. And x is going to be the stone space of this Boolean algebra. So these guys are clopen. And the most important part over here is for every CUV, there is a subset, a clopen subset of x that is going to split the sequences. It's going to split not the sequences, but the rings. These A alphas are decreasing, so you can consider these rings. And the U's are meant to be to split the rings. So one U is going to contain, let's say, the even rings, and it's going to avoid the uneven, the odd rings. This is in order to have that this guy that I haven't mentioned is not going to be close, but it's going to coincide with the radial closure of omega. All right. What is more important here is the technique. And this technique involves a matrix iteration. So I'd rather I want you to focus on the right-hand side of this screen. What is a matrix iteration? So one finite support iteration is like only one axis. And the iteration is you're having a generic filter over and over the previous model, another generic filter over the previous model, etc. So over here we have two directions. The properties are at any point in this matrix, the next poset in the next extension is going to be CCC. It satisfies the countable chain condition. Meaning anti-chains are at most countable. Next property says, I think I missed the other property. Number 2 says horizontal lines are finite support iterations as usual. The third property says something about the columns, and the columns basically the smaller posets, the queues, are embedded into the bigger queues. And this is what we call a complete embedding. It is not really a complete embedding, but we can just think about it. And columns for limits ordinals over here, the next guy is going to be just the union of the previous ones. As I mentioned, it's not really important understanding the structure of matrix iterations, but the power or the consequences of these posets. So I'm going to tell you what the posets are. For the first column, we just take the trivial poset. This doesn't do anything at all. For the next column, I mean, over here we have an extension, and that means we are creating these new posets in the extension. They're gonna be what we call the Heckler forcing. The Heckler forcing adds a dominating real. A dominating real means it's bigger, it's a function from omega to omega, bigger than any other function in the ground model. All right. These guys will add this family of the 8 alphas. Next columns, they're very weird, and they're gonna add these U's that are gonna split the rings. All right? But these gammas are gonna be up to omega 2. And after omega 2, we're gonna have posets, which are called the Matthias forcing, and these are gonna add the splitting reals. So the splitting number is gonna get to Aleph 3. So we're adding in all these blocks, we're adding a lot of functions from omega to omega that are splitting reals, and we're adding omega 3. All right. So the first column added this family, and it's going to be decreasing. The last part, the last interval from omega 2 to omega 3, is going to get the weight of x less than the split number. All right, sorry. Okay, and that's it.
Okay, thank you. And now let's ask some questions. Please.
Yeah. So it looks yes. So it looks like continuum Acosta decides this entire story. What happens if you assume something like Martin's axiom instead? Does that decide in the opposite direction?
Martin's axiom gives you the pseudo intersection number equals the continuum. What are these guys? This, the pseudo intersection equals the continuum, comes from Martin's axiom. So for example, 4 implies 3, 4 implies 3. We have that property. But you don't get the full pseudo radiality under Martin's axiom.
and like blush class. So if you only consider finite sets, it becomes not very interesting problem.
You mean finite spaces?
Yeah.
They are pseudo-radial.
Okay. Thank you. Other, yes. And over.
So looking at this kind of sequence of relationships between pseudo-radial and all the way down to sequentially compact, is there any interesting relationship in the locally compact case between pseudo-radial and any other topological properties? I guess like sequentially compact would fall off, but anything else like separability or anything?
I don't know. I don't know. You're right. We can define, for example, local pseudo-radiality. I would think about it as every point has a local a neighborhood, maybe a closed neighborhood, or not necessarily close, an open neighborhood that is pseudo-radial. And what can you get for the entire space? I don't know. I don't know. I haven't seen any local property around this pseudo-radiality thing.
Thank you.
Good question.
Just
I have kind of another regulatory question. Are there any like fun sort of consequences in analysis?
Absolutely, and in algebra and whatnot. But you mean for the forcing or for the pseudo-radiality?
Yeah, I mean, for any part of this to collapse, I'm just wondering if there's sort of some fun statement of analysis that could be, that's true if like one of this tower here, two of these tower things are the same or something like that.
Okay. For pseudo-radiality, well, these concepts are more for general topology definitions, but maybe I can say, of course, forcing has a lot of applications to analysis and group theory. But also some of these numbers have a strong connection to analysis. For example, for the almost adjoint number, and there are many more that I haven't defined here, but there are many other cardinal invariants that are strongly related to analysis. Maybe I can share with you later.
yes.
Are all these between omega 1 and the continuum?
Yes.
Is known the order among them?
Actually, that's a huge part also of set theory, how these are related. Some of them, for example, B and D, B is less equal than D. And a strong labor is, for example, to come up with a model, a forcing extension in which B is strictly smaller than D. Some others, I don't remember which, but some others are incomparable. That you cannot decide like which one is bigger, or in some models you're gonna get this bigger than this one, and weird things. And the matrix iteration technique, there are like 3 dimensions matrix iteration, and many more. And what they can do is to split, to have strict inequalities among cardinals simultaneously, and you can get like 8 different, you can make the distinction of 8 cardinals, for example.
Thank you.
Else? Somebody from Zoom, maybe? Maybe somebody from Zoom have a question from the previous talk. Didn't ask. Okay, then let's thank Hector again.